Welcome to 2.5. Today we're going to talk about lines and planes, and this is probably one of the most useful sections in the whole semester. A line is determined by a direction vector and a point on the line. And if you have those two things, the vector equation of a line is written here, and that's actually three different equations. If we write those equations in parametric form, we get these three equations here. And so let's solve some problems using those equations. The first one, we're given parametric equations for a line, and we want a point on the line and the direction vector for the line. Well, we can solve both of these at once. Let's write x as 2 plus -1 times t, and y as 0 plus 4 times t, and z as 7 plus 0 times t. Then for part A, a point on the line, if you compare these three equations to the three in the box above, you can see a point on the line is simply 2, 0, 7. For example, you could take t equal to 0 and get 2, 0, 7. And then for B, the direction vector for the line, or a direction vector, you want the coefficients of t, -1, 4, 0. So it's that easy. Okay, next one, find parametric equations for the line through this point parallel to this vector. So our x naught, y naught, z naught is given as 3, -3, 1. And actually our direction vector is also given. If our line is parallel to v, then that will be the direction vector of our line. So v is going to be 1, -1, 0. I'm writing that in component form. I think it's easier. And then our three equations are x equals 3 plus t, y equals -3 minus t, and z equal 1 plus 0t, so z equal 1. Okay, and we're moving up in complexity here. The third one, we want parametric equations for the line through these 2 points using P as base point. So here's P, here's Q. Want the line through those points. The direction vector is going to be the vector PQ. And we want to take P as our x naught, y naught, z naught. All right, so our direction vector, V, is PQ. And that's, remember, you want to take the Q's and subtract the P's. So we get -2, -2, 2. And our x naught, y naught, z naught, we're told to take P as the base point. So that's 1, 2, -1. And so in parametric form, this line is x equal 1 minus 2t, y equal 2 minus 2t, and z equal -1 plus 2t. Now, as a vector equation, this is just an alternate way to write it. We would write pointy brackets and put p in the pointy brackets. So 1, 2, -1, and then t times the direction vector, -2, -2, 2. So some of your homework questions want vector form and some want parametric equation form. Okay, now let's talk planes. A plane is determined by a point in the plane and a normal. So if P is x naught, y naught, z naught, and x, y, z is any other point in the plane, then the vector from P to x, y, z is always perpendicular to n, and that gives us this equation here. And when you expand that out, you get this, the general form of an equation of a plane. And this is, I call this the use me every day equation because you are going to use it almost every day. And again, the only things you need are a point in the plane and a normal to the plane. All right, so let's do an example. Find the general form of an equation for the plane perpendicular to n and passing through P. So we're given our ABC in the formula above. That's the vector n, 1, -2, 3. And we're also given our x naught, y naught, z naught. That's the point 1, -1, 2. So we do the use me every day. 1 times x minus 1 minus 2 times y plus 1 plus 3 times z minus 2 equals 0. That's the use me every day. And then if I distribute and combine like terms, I get x minus 2y plus 3z equals 9. And you can double check my arithmetic on that one. Okay, let's go the other way. There's a very cool theorem that tells us if we have the equation of a plane written like this, then a normal vector is simply the coefficients of x, y, and z, a, b, c. And that's going to come in very useful. So for example, A, find a normal vector to the plane. So for part A, that's super easy. We just pluck off the coefficients, 2, 3, -7, because that equation's already in the correct form. And B, find one point lying on the plane. So for B, we need a point on the plane. And the easiest way to get that is to set two variables equal to 0 and solve for the third. So for example, if I were to set x and y equal to 0 in this equation, and I solve for z, I get z equals -4/7. So that would be one point lying on the plane. Or I could set y and z equal to 0. That might be easier because that way I get x equal 2 and I don't have fractions. And finally, I could set x equal to 0 and z equal to 0 and solve for y, and I get 4/3 for y. Okay, let's do another one. Find the equation of the plane through this point parallel to this plane. Well, this plane, by our cool theorem, has normal n equal to -2, -7, 8. And if our plane is parallel to that plane, then our plane has the same normal. So that's what we want to use as our ABC in the Use Me Every Day. And we're given our x0, y0, z0. That's 7, -1, 6. So if we do the Use Me Every Day, we get -2 times x minus 7 times y plus 1, and then plus 8 times z minus 6 equals 0. And I do want to see that line in your work whenever you find the equation of a plane. I want to see that, and then distribute -2x plus 14 minus 7y minus 7 plus 8z minus 48 is 0. And then move all the constants to the other side. -2x minus 7y plus 8z equals 41. And there it is. Okay, angles and distances. When we find the angle between two planes, we simply want the angle between their normals. And so this equation here is the same equation we had for the angle between u and v, except that there's an absolute value on the top, and that ensures that we get an acute angle between the two planes. For the distance formulas, I've got a little picture proof beside each one that you can read through, but I want to stress that you need to know what all these letters are. In each case, Q is the point given. And for a line, the distance from a point to a line, you will need a point on the line, and you will need a direction vector for the line. For the distance between a point and a plane, you will need a point on the plane, and you will need a normal to the plane. And then it's just plug and play. So, for example, suppose we want to find the distance from this point Q to the line given by these parametric equations. So the first thing we want to do, if I started this out on the solution to save time, the first thing we want to do is write down the formula we're going to use. Length of PQ cross V over the length of V. Now we're given Q, we need P. P is a point on the line. And so to get a point on the line, we can just set T equal to 0 in the parametric equations to get 0, 1, 0. And you should write down what P is. So I wrote that down. Let P be a point on the line. And we need V, a direction vector of the line. And so now I want the coefficients of T. 2, 2, 2. All right, PQ is the vector I get by taking the Q's and subtracting the P's. So that will give me 1, 0, -1. Now I've already crossed PQ and V, and you should verify that fact that this is the vector you get. And so now we're going to need the length of PQ cross V, that's the square root of 2 squared plus -4 squared plus 2 squared which is the square root of 24. And we're going to need the length of v, which is the square root of 2 squared plus 2 squared plus 2 squared, which is the square root of 12. And finally, our distance, which is the length of PQ cross V, divided by the length of V, is the square root of 24 over the square root of 12, which is the square root of 24 over 12, which is root 2. Okay, and that is the end of this section.